Okay, and we're starting. So last time you introduced the derivative and spoke about some of its properties. We saw the derivative is so-called. And we saw that it was a particular limit. So for f of x, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. If it exists, is its derivative. And we saw that it meant several things. This gave us the slope of the function. It also spoke about the slope of the tangent lines of the function. We saw that it was the instantaneous rate of change. That's how we developed it. We wanted to find the speed at which f was changing at a particular point. How fast f is changing with respect to x. So that was the derivative. We also derived the power rule. A very basic version of the power rule, which basically says if we want to take the derivative of a function that looks like this. So this means the derivative with respect to x up. And then I want to take the derivative of something that looks like that, like something raised to a power. Is nx to the n minus 1. This was called the power rule. So for example, if I wanted to find the derivative of x to the 7th, that is 7x to the 6th. And basically how we interpret that function compared to this one is that it tells us about the slope of the function or the slope of the tangent lines of the function or its rate of change of the function, how fast it's changing with respect to, how fast the y coordinate is changing with respect to the x coordinate. Okay, so we had all of those. We also saw that we had a constant factor rule. So this is saying that if we have the derivative of a constant times a function, you can factor the constant out. This is the derivative of the function. We also saw the sum rule, which says if you're taking the derivative of a sum of functions, then it's just taking the derivative of the individual functions and sticking them together. And using those, we could find the derivative of some more complicated functions than simply something that looks like this. So we can apply these to several situations. So I could say, what is the derivative of 3x to the 4th plus radical x? I could just think of this as the derivative of 3x to the 4th plus x to the 1/2. And I write it like that because there's a rule I want to apply, so I want to make sure my functions look like that rule. And then I would get 12x cubed plus 1/2 x to the minus 1/2. Okay. And we also saw some more properties of the derivative where a derivative does not exist. Also, and you needed to know this for the test, of course. Well, everything I said you need to know for the test. Also, we know that derivatives don't exist at 1, sharp corners, 2, where f is not continuous, and 3, where f has vertical line. And this also, well, I don't think we mentioned this last time, but it's nice for me to just say it at this point. So if you're looking on a graph, for example, any sharp corner, right, so anything that looks like that, derivative won't exist there. Any hole or gap or jump, the derivative won't exist there. And anywhere the function goes vertical for like a split second, the derivative won't exist there. This suggests a theorem that I'm not going to prove, but it's nice to just state it and state the fact that the opposite isn't true. If f is differentiable at a point, meaning you can find the derivative there, then it is continuous. There's another way to say that. If f is not continuous at x, then f prime does not exist at x. And it's also important for you to know at this point, and we did an example where this was the case, so it's not anything new technically. It's important that you know the converse is not true. Right? So the converse of some mathematical statement is the opposite statement, which means just because it is continuous doesn't mean it's differentiable. F is continuous does not mean it's automatically differentiable. And we saw that, you can see that here, because of course it's continuous at sharp corners, but it's just, you can't actually find the derivative there. And we did an example here with y equals absolute value x at x equals 0. Right? So that was when we had the V-shaped graph, and we said the derivative actually doesn't exist at the origin, because if you try to find the derivative limit, it did not exist. But you are continuous there. So if you can find the derivative, it means the function is continuous, but it doesn't always work the other way. And so ultimately that talks about the 3 cases and the relationship between the derivative and continuity. So if you're drawing a graph, and I believe there was a problem like this on the test, if you're given a graph, you're supposed to be able to spot where it's not continuous. And those are automatically points where it's not differentiable, so you just copy those answers down. And then in addition to those points, you look for like sharp corners or anything like this. Okay, so that's just kind of a small recap of what we were doing last time, just to get everyone back up to speed what we were talking about. We are going to learn more about derivatives now, how to differentiate even more complicated functions. Let's actually do some motivation. I'm going to talk about something called the chain. That's not working. So, quick motivation. So with what we know so far, how would you find the derivative of something like x squared plus 1 squared? Well, we know the power rule, and we know that derivatives distribute across sums. What are you talking about? It sounds to me like you're applying the chain rule. But we don't know it yet.
Oh, okay.
We don't know the chain rule yet. I haven't introduced it yet.
Oh, okay.
How would you do that if you didn't know the chain rule?
The power rule, you would,
Okay, so first it's important to know that the power rule does not directly apply. At least not directly. Okay, right? So if you're looking at that, the power rule doesn't apply, because the power rule says the derivative of x to a power. Right? As in specifically x. Right? Here you don't have x to a power, you have something else to a power. So you can't apply the power rule right away. What would you do? Yeah?
Wait, we're doing the chain rule?
No. How would you do that if I didn't tell you the chain rule?
I would do, like normally you would just square the.
Okay,
you know,
and what would you get?
Two x.
Right, so you could do that. You could just square it out. And now you can actually apply the power rule to each individual, right? And we know the sum rule, so the derivative distribute across the sums. So now I can differentiate each of these separately. Okay, so that would be 4x cubed plus 4x plus 0. We saw that the derivative of constant is always 0. Okay, so that's one way you could do it. But, okay, so now here's where the motivation is going to come in. What if I asked you to do that? Now you wouldn't want to do the same kind of method, right? Right? Because expanding that to the 50th power, you're going to get 51 terms. It's not really something you'd enjoy doing, and you probably take the entire test doing it, right? So while with smaller powers we can do that. And sometimes, even if the power is not that big, it can be problematic. So I could ask you to do this, right? And that's just a half power. That's not really a big deal. But how do you expand a half power? It turns out that you'd actually need an infinite number of terms to expand a half power. So that's, of course, not going to be what we want to do. So here's where the chain rule comes in. So the chain rule deals with situations like this, when you kind of have a rule that you want to apply, but you're not exactly in the right situation because the rule tells you how to deal with it if there's just an x, but you have something instead of just an x, right? So instead of x squared, we have an x squared plus 1, right? All squared. So we can use something called a chain rule. So this says, and of course you have to, you're never gonna have to worry about this, but I guess that we sort of complete have to say this. Suppose if f is defined at g of x, if f and f prime is defined at g of x, if f, g, let's put this are differentiable, and f prime are defined g of x, then you can actually find the derivative of something that looks like this. Right? So you have a composite function, where you have one function kind of plugged into another function. And I'm going to relate that to this pretty soon. But here you kind of have an inside function, kind of like this guy was an inside function. Right? So here you have some function inside some other function. Right? So here you have a square function, right? This is a function that's squaring stuff. You can think of that as working on the outside. And there's someone plugged inside that square. Right? So here's like you have an inside function here. That's not just x, it's something else. And you have an outside function. So you have some function operating on another function. And you want to be able to differentiate something like that. The rule is, and we're not going to prove it because the proof is actually a bit subtle. You are supposed to differentiate the outer function, leaving the inside alone initially, and then you would multiply it by the derivative of the inner function. And doing that is called the chain rule. So differentiate the outer function times derivative of inner function. Okay. And initially, when you're differentiating the outer function, you leave the inside alone. Sometimes I see people start to do the derivative inside here. You're supposed to leave the derivative, the inside alone initially, right? You take its derivative afterwards. And of course, you might have to do parentheses here as well. If you have several terms in the G. So I kind of marked that up. Let me write it down clearer here. I.e., there's something called the chain rule, and this is now something else that we have to memorize. It says that the derivative of f of g of x is f prime at g of x times g prime of x. There are other ways to think about the chain rule, but this is the only way that we'll care about. I mentioned the other one in the handout. So this is used to differentiate composite functions. Okay, that is functions in functions that have other functions inside them. Right. So we're talking about, for example, if we looked at x squared plus 1 squared, right? We could have thought of this as, well, I have one function that's an x squared, and I have another function that's x squared plus 1, and then this guy, the x squared plus 1 squared, would actually be equal to f of g of x, right? If we remember what that means. Take this guy, plug it in that guy, you'd actually get this function here. Similarly, if we had x squared plus 1 to the 50th, what that means is there's an outer function, just raising things to the 50th power. There's an inside function which squares something and adds 1. And then this guy would end up being the outer function evaluated at the inner function. and you can kind of look at also, say, the square root of x squared plus 1. So this means your f is just the square root function, your g is just x squared plus 1, and so this guy is actually just f evaluated at g. Right? So the thing that all of these functions have in common is that you can think of them as composite functions. You have guys plugged into them, right? So you have something that is not just x, right? So you have something in here that's not just x, it's a whole other function. Similarly here, it's not just x. Similarly inside here, it's not just x. Right? And that's kind of going to be when you would want to use the chain rule. How do you know when this rule will apply as opposed to the power rule? It's when you have a rule, but the x in that rule is replaced with something else. So let's actually write that down. When would you apply the chain rule? Okay. Couple things here. One. You actually don't have to worry about that. It might be a question on your mind. You don't have to worry about it too much. It turns out you can always apply the chain rule. And if you don't need to, if you didn't need to really, you won't have much consequence from doing it, right? There are some other rules that I'm going to talk about where if you apply them where you don't need to, it can actually make your life a lot harder. But the chain rule isn't such a rule. For example, we could talk about what's the derivative of x squared, right? Let's say we thought of this very complicated, like, oh my, like, this is the derivative of x squared, you know, like there's an inside function, right, which you wouldn't normally think about that. But if you were to do the chain rule here, what you would do is you would take the derivative of the outside function, right, leaving the inside one alone, and then you'd multiply by the derivative of the inside function, which is going to be what?
1.
It's going to be 1, right? So worst case scenario, if you apply the chain rule when you don't have to, the worst thing that's going to happen is you're going to multiply by 1. So it's actually not something you have to worry about too much in the first place. But not applying it when you need it can be a problem. So you should know when you definitely need to do it. And how do you know in those cases where you definitely should be using the chain rule? So first step is to have all the basic rules memorized exactly. Not a huge deal in this class because the only other rule besides the ones I'm talking about today that we will know is the power rule. So not that crazy. But I have seen this problem come up. For example, in one of the finals, there was a function that we are never going to learn how to differentiate that came up on the final, but it came up in the calculator section. So the theory was students will just know hey, that doesn't apply to any rule we know, let's just plug it into the calculator. So the first thing is to have the basic rule memorized exactly. Here I'm really kind of talking about the power rule. It's kind of the only rule you would, kind of the only special, specific rule that you would know here. And by memorizing it and knowing it exactly, keyword on exactly, that means you should know that, hey, there's just an x here. Hey, this is a constant, right? If you don't have a base that's just a single variable, and you don't have a power that's a constant, power rule does not apply. So for example, you should know, if you wanted to find the derivative of, I don't remember the exact problem, but this was on a past final, and something like this was also on the test, where they did that, right? And the trick was, you're supposed to know, we don't have a rule for that. That's not something I can do, right? There is a way to do it, but it involves functions that we're just not talking about. You need to know about logarithms and exponentials to do a problem like that. So you can't really do that by hand. You should be able to recognize that, hey, I cannot do this by hand, right? You should know that power rule does not apply. And how you would know that the power rule does not apply is because you know the power rule super well, and you realize that in the power rule, the power is a constant, whereas here it is not. Therefore, the rule does not apply. So you need to know your rules very precisely. So that's the first thing. So the first step into knowing when you need to know the chain rule is to first know all the very basic rules, all the simpler ones that are simpler than the chain rule, know those very well, right? And so basically, the second step would be is to notice when the x in those rules are replaced by something else. Okay, so so if we want to find the derivative of x squared, that's no problem. That's the power rule. Right? Because here I have just x. Here I have a constant. So I'll just apply the power rule, because it looks exactly like the rule. However, if you have something like this, yes, the power is a constant, but it's not just an x now. Right? You see the difference? Right? In the place of x, there is some completely new function. So instead of just x squared, we have this whole function squared. X is replaced by the x squared plus 1. So it's not just x squared. There's a whole like messy thing all squared. So if you see something like this, you would opt for the chain rule actually. Do I want to do some more examples? Yes, let's do some examples. Let's do some examples. Let's make sure we understand this before we move on. So you might have needed ideas like this, and what I'm going to talk about for the bonus for the test today. Find these derivatives. X squared plus 1 squared. We did that already by expanding. Let's see if we get the same thing when we actually use the chain rule. What if I put the 200 power? What if I put a square root? What if I put a cube root? What if you see something like this? And what if you see something like this. We're gonna do all those, start writing them down. You can probably start the first three, and then we'll actually do it together. Okay, let's jump into it. Okay, A, do the chain rule right now. So, Michelle, what you were saying before, obviously read ahead trying to get those bonus points, yeah.
So you start with the 2, like you bring 2 out,
Mm-hmm.
and then you parentheses x squared plus 1. And then times, well, because you leave it alone because you know the minus 1, so you just leave that alone. Then you times it by the derivative of the inside.
Okay, which is?
2x. And then now you multiply them.
Right, you could multiply these guys here.
Just the outside first, and
In general, you don't have to multiply the inside because usually the power here is going to be something wacky that you can't bring it inside anyway. But you could, just to check with what we had before, you could notice that if I were to multiply this out, this would give you a 4x cubed plus 4x, and you'll notice that that's what we got last time when we actually did it the long way. Right? So I kind of threw this example in there just for you to, you know, have some confidence that what I'm telling you is the truth, because we didn't prove it. So it did work out here, and that would be how you do the chain rule. So the idea here is you look at this and you say, oh, it's not just x squared. There's a whole function squared. So what you're going to do is for a second you're going to pretend that that thing is just an x, and you're going to differentiate around it. This is called differentiating the outer function. But then because it's not just an x, you have to multiply by the derivative of the inside. Right? And this process is called the chain rule. Okay? You say you have applied the chain rule in order to do this.
No.
I have no.
It
It's
did
slanted?
move. Yeah. Okay. Any questions on this, the idea that we just applied? Because eventually we're going to be applying these ideas very quickly. So, and you can apply multiple ideas at once. So I want to make sure that everyone has this one like solid. Like any questions on what happened? Yeah.
Yeah, where did you get the 2x from, like, after the parentheses?
Okay, so here, the x squared plus 1, this is the inside function.
Yeah.
You would recognize that because it's in the parentheses
Yeah.
and there's a square around it. So you multiply by the derivative of the inside.
Okay.
Right? So in this case, it's like the x squared plus 1 was your g of x. Right? And so this out here is the g prime of x. Okay? Your f is like the square function. So you differentiate, you find f prime, which the power rule tells you how to do that. Leave the inside alone, but then you have to multiply by the derivative of the inside. Any other questions?
This fell out.
I don't understand. Why do people insist on sitting there if you just keep kicking the camera? Why not just sit somewhere else?
It's my jacket.
I'm going to sit here just so I have the opportunity.
Wait, where's the?
It's fine. Just leave it.
Oh,
alone.
okay.
Okay. So maybe this would also make it. So this isn't much more complicated. I'm just redoing a very similar version. So what would you say happens here?
200 x squared plus 1 times 2x.
No, that's wrong. What happens?
Oh,
Huh? There's something missing.
oh, you minus it by 1?
Minus what?
The exponent of 200?
Okay, and what happens? So remember, there's an insight. If you were to differentiate, if I asked you separately, okay, this was the problem. Differentiate x to the 200. How would you have done it?
I would do
This
100x.
What would happen?
200x power to 199.
Right? You're doing exactly the same thing here. Right? So here is this guy. Right? So you're going to differentiate the outside by applying the power rule, which means you're going to put the 200 of the thing to the 199. So that's important, because that's what you would have done here. Right? That's what you would do if it was just an x, but it's not just an x. It's x squared plus 1. Now you see that it's not just an x. You have to multiply by its derivative. And so that's 400x times x squared plus 1 is 199.
Wait, so what do you do after? That's just the final?
Come again?
Do you do anything after? Like distribute the 400x?
How would you do that? This has a power 199.
So you just leave it?
This doesn't. Yes, that would be the answer. Pretty much the simplest way you can do this one, actually. Right, so remember, and the reason why is because there's a law of exponent that say the only way I can bring something inside of a parentheses with a power on it is if that thing itself has the same power. Right? So if I have something to a power, the only way I can multiply this guy inside and put him inside the parentheses, that thing has to also have the same power. The 400x does not have a power 199, so I cannot bring it inside, because that would violate the law of exponents.
Oh, and since 200 was just no.
The 200 is just, yeah, the 200 is just, it's 200 times this to that power times. So, because multiplication can work in any order, I can take the 2x and multiply this to get the 400x, but I can't move it inside the parentheses because the powers don't match. because the power was 1. The power here is 1, so I can't.
Okay, okay.
Okay, what about this one?
So you do x squared plus 1 to the 1/2.
Sure, you rewrite it?
And when you rewrite it, it's 1/2 to the x squared plus 1. And then 1/2 minus 1,
Which is?
negative 1/2. And then to 2x times 2x. And
Right.
multiply the 2x to the 1/2,
Mhm.
which is x, yeah.
Yeah, and that'll be fine. And if it's a multiple choice, you should be aware that they could have written the answer in another form. It could be that, but, I mean, if you're writing it on a test paper, writing it out longhand, that'll be fine. Okay, what if we had a cube root? How do we deal with that?
Just to the third.
Can't pull one over on you, huh? She's like, I see your tricks, come on. Yeah, that's the 1/3 power. So there's the power rule for that, right? So that's just something to a constant power. It looks almost like the power rule, except there's an inside function, it's not just an x. So what I do is I pretend this is just one thing for now and differentiate around it. So I'm gonna put the 1/3 down, subtract 1 from the power. What's 1/3 minus 1? Minus 2/3, right? So remember, whenever you have a fraction you want to subtract 1, just subtract the denominator over itself, right? So it's 1/3 minus 3/3, right? So you get minus 2/3. You leave the inside alone. Because that's not just x, you need to multiply by its derivative. So that would give you 2x/3 times x squared plus 1 minus 2/3. Okay, what about e? Ideas?
Do you have to bring the 2 minus 3x to the top?
Okay, how would you do that?
So it will be 2 minus 3x to the negative 1/2.
What happens to the 4?
Multiply that?
Yeah, it just stays there. Okay. Now we didn't differentiate. It's important that you realize that all you just did is an algebra trick to rewrite it. Okay, so now how do we finish?
Multiply.
Minus 1 comes down, makes it a negative 4. Leave the inside alone. What happens to the power?
Minus 2.
So the inside stays, and then what? Multiply by derivative of the inside. Derivative of 2 is 0. Derivative of minus 3x is minus 3. So this ends up being 12 times 2 minus 3x minus 2. Or it could be like 12 over 2 minus 3x squared. Like in general, I don't care if you write the answer like that, but on a multiple choice test, the answer might be written in that form. So you should at least know how to go from your answer to the answer in another form.
How would you, for this, for D, how would you like flip it down, like with the 3?
Oh, so here you'd have to remember that rule, that x to the a over b is the b root of x to the a. So if that's your answer, in the multiple choice might look something like this. If they decide to rewrite the answer with a radical, it would be 2x on top over the 3's still on the bottom. And then because there's a 3 in the denominator, that would give you a cube root. And then the 2 on top will give you a square. So this would be x squared plus 1 squared. So that's another way to write it. f. What do we do here?
Where?
You said it's x cubed minus 2x plus 3,
To the one negative.
right? Minus 1/2, right? Because that, it's square root, so it's a half power, but because in the denominator it's minus half. So laws of exponents, right? So I just applied an algebra rule, I didn't apply the derivative yet, so the derivative is still there. Then,
Then it would bring down negative one
Mhm.
x cubed minus 2x plus 3, because it stays the same, and negative 1/2 minus 1.
which is?
Negative 3, 2.
Okay,
And
we're done.
then, no, you have to do the g prime of x, so like
Fine. Now everyone's tired. Felicia.
3x squared minus 2.
You write like that?
Probably
Then
like
you
this.
distribute it.
And then you distribute, yeah.
Distribute what? Well, it's important that you remember that, yes, there should be parentheses here. So here they're super important because we have two things. So you may have to distribute. In this case, I wouldn't distribute. I would just, again, just like the last time, just multiply across. So I have like minus 3x over 2 times. I wouldn't like create two terms or anything like that. Unless there's a very special reason for doing that, but usually there
Oh,
won't be. Okay.
That's the answer.
Yeah, that's fine. I mean, you could also rewrite it by bringing that thing down and making it the square root of that thing cubed. By applying a similar rule here, you just have a cube here and a square root. I'll have more examples where we'll actually be applying the chain rule as well in conjunction with something else, so we'll stop there with the examples for now and move on to some other rules. So, let's look at the derivative of x squared. We know that that is what?
2x.
We know that's 2x, right? Now, what if we did this? I'm writing it in red now because it's the wrong thing, okay? So let's say we have x squared, but instead, for some reason, I want to think of this as x times x.
That would be
And so now, you might think to yourself, derivatives distribute across derivatives distribute across products. And so you might test this theory, right? Because it distributes when there's a plus sign there. Would it distribute when there's a
it'll be 1
multiplication
plus
sign?
1.
So if you differentiate that and then differentiate that and then just multiply them together, what you would get is the following, right? You would actually get
1 times 1.
ddx of x times ddx of x, which is just going to be 1 times 1, which is 1, which we know is the wrong answer, right? We already know how to do that, right? So that's just a very simple example to show you derivatives do not distribute across products, right? So they're not like limits or powers, right? They have a different property when it comes to products. And because a product is kind of inextricably linked with division, it also stands to reason that it won't work with division either. So this shows derivatives do not distribute across products. very important for you. You know, if you have things multiplying, there's a whole rule that you have to go through. So now you might ask yourself, so how would we differentiate a product? How would we differentiate something like this? F of x times g of x. How would you actually find the derivative of such a thing? Yes, I know you're all great students and you read ahead, but let's actually figure it out together. Let's pretend we don't know the answer. Okay. So one reason why the definition of something is important is because a lot of times when you're in a weird situation that you don't know how to deal with, you go back to your roots, you go back to the definition. And so you might say, okay, let's use the definition. If we wanted to find the derivative of f of x times g of x, what we would do is find the limit as h approaches 0 of the function with x plus h minus the original function all over h. And now we're going to compute what this would have to look like. How would we actually make sense of such a thing? And so in the first case, well, what we're going to do is we're going to do that trick, kind of a similar trick to what we would do when completing the square or many other things. We kind of write something in that's not there, but we do it in a very convenient way. So here's what we're going to do. We're going to add and subtract something that's going to conveniently make things look nicer. Okay. So what I'm going to do is I'm going to subtract f of x times g of x plus h. Right. That's because I kind of don't like this g of x plus h stuck to the f of x. I kind of want to separate the f's and the g's. So I said, hey, let's add something like this so I can like factor this guy out and leave f's alone. But I can't just randomly add something that changes the value, so I have to subtract it, add and subtract it again. And now we remember we can actually split fractions across the numerator of a fraction. Okay. So I can split this this big fraction into two fractions. I can split it into this one, and I can split it into that one. And so I would get the following. Plus that. And now, as I said, let's factor off the guys that we don't want to have to worry about. So this g of x plus h here is a common term. I can factor that off. I'm going to factor that out, and I'm going to move it to the right, just because. Plus, here, f of x is a common term. I can factor that off. Let me factor that off to the left. And now I'd be left with this. That was g of x plus h. But now I just have a limit, and we know that limits are among the nicest things ever. They distribute across both sums and products, okay? So it turns out that I can think of this as the limit as h approaches 0 of f of x plus h minus f of x over h times the limit as h approaches 0 of g of x plus h plus limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. Okay. And one at a time, what is this guy? Right, this part here, the first limit.
The definition.
That's the definition of the derivative for f. So the first part is just f prime of x. Now, as h approaches 0, this function, right, I just plug in h equals 0, that's leave me with g of x. Plus, here, limit as h approaches 0 of f of x, well, there's no h, so it's not going to do anything at all. And here, now I have the definition for the derivative of the function g, that is g prime of x. And so it turns out, to differentiate something that looks like this, that's how you would do it. And this is called, because we have to differentiate a product, it's called the product rule. So let's just write that down. Something that we call the product rule. It says, if I want to differentiate, and of course I'm assuming the functions individual are differentiable, etc., blah, blah, blah. And they're defined at x, whatever. So to differentiate something that looks like f of x times g of x, a product, what we would do is we would differentiate one of them, leave the other one, plus leave the first, differentiate the second. Right? Take one derivative at a time and you add them together. This is called the product rule. Right? So this is used to differentiate products. And you could memorize it in shorthand. I don't mind at this point, because sometimes writing that parentheses x might be annoying. But you could memorize this as f times g is f prime g plus f g prime. And this is called the product rule. So you differentiate one function at a time and you add them together. And again, I mean, I did a long proof, but does this actually work out? Let's do it with our silly example to see if it actually works. Right? One where we actually already know the answer. Right? So we want to differentiate x squared. We know the answer should be 2x. Let's just make this needlessly complicated and write it that way. And then apply this rule. Well, if I think of this as two functions being multiplied, let's say I call this one f and call that one g, then according to this rule, I should have f prime times g, and then add the f times g prime. And so let's actually do that. Well, if f is x, f prime, well, we should know is 1, times the g is just x, plus the f, well, the f is just x, times the g prime, well, g is x, so g prime is 1. So here I get x plus x, which is 2x, and yeah, that checks out. That agrees with what I know it should be. Now, of course, you wouldn't do the product rule in this case. I'm just illustrating to you that, yeah, it works. It's consistent with what we've already done. Let's deal with divisions. So again, that's in a box. That's what you need to have memorized, and you need to know when you have to apply it, which I'll talk about that in a little bit. what about if you had a division of functions? We have reason to believe that the derivative would not actually distribute. But here, I'm not going to need to go back to the definition. I'm just going to actually do a similar technique to what we were doing in the last set of examples, and I'm going to rewrite this. I'm going to rewrite this as f of x times g of x to the minus 1. And now I can apply the product rule. And so that tells me I'm going to differentiate this one, leave that one alone. Let's write it out longhand first. F prime of x times this one plus, leave the f alone, times, well, how would you differentiate this guy?
So you do that power rule to it?
Right, you have to do the one, minus 1 comes down, subtract 1 from the power. Is that it? You have to multiply by the derivative of the inside. So the g in this case is like an inside function. So let's rewrite this in shorthand for a little bit. So this is f prime times g to the minus 1. This will be minus f times g prime times g to the minus 2. In other words, this is f prime over g minus f g prime over g squared. I want to combine these, so I can multiply by g over g to create a common denominator, and then I would get f prime g minus f g prime all over g squared. And it turns out then, to differentiate something that looks like this at division, the result would be something like that after I simplify and combine fractions. Combine fractions. It might not be simplified fully at that point. So this leads to the quotient rule. Right. Quotient is a fancy name for the result of a division. It says if you are differentiating f divided by g, of course your g can't be 0, we're assuming our functions are defined and they're differentiable, then this is f prime g minus f g prime over g squared. And there are many mnemonics for remembering this. Some of you might know some already. Some people might talk about low d high minus high d low over low squared, where this is the high function and that's the low function.
That's how I learned.
So you could have learned it that way and it's fine. However you remember it, make sure you remember it in the right order, because this one has a minus sign in it, so the order in which you do things actually matters. The product rule doesn't, because you're multiplying things and then you're adding them together. You can do any of those in either order. The quotient rule though, the order does matter. So you have to take the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That's kind of how I remember it. I literally say that sentence in my head every time. Like the low d high is fine, but it's too much translation for me. I rather go bottom and top. That's kind of already.
That's how I learned.
Right, you don't want your brain to go through extra steps, so. And that's the quotient. Let's actually do some examples. And while doing some examples, I'll talk about when you may or may not want to do the quotient. So, examples. And I mentioned the low D high and the one I care about, whatever. Okay, so I want you to differentiate these. Yeah.
So for the first one, because it has an x split, you don't have to differentiate that yet, right? That's just like your g of x at 2x plus 1 to the fifth.
Yes, so we're gonna go through them. I was just waiting on everyone to copy them down. 2x plus. I think it's fine. Okay, so yeah, to go with Michelle's question, here notice that you kind of have a situation that we don't have before. So first of all, the power rule itself doesn't apply, but it doesn't apply for a couple of reasons. One, we could technically apply the power rule to x squared, but it's being multiplied by this guy. This guy, we can't actually apply the power rule directly, we have to apply the chain rule. But, so that kind of suggests to you, hey, this is really two different situations hitting me here, right? I have two very different functions. Here's one function, and here's another function. I have two functions multiplying each other. I can call one f and one g. So here, notice we have a product. Now, actually, the first thing I would actually look to see is, could I actually simplify that so I don't have a product? But here, no, not really. One is a squared power, one is a fifth power, so I can't actually really do anything without too much work. So I would just, so simplifying, annoying. So I would use product rule. So now, according to the product rule, this says to differentiate two functions being multiplied, I would differentiate the first one, multiply by the second, plus leave the first one, differentiate the second. Okay, so that's what the product rule says. And so now you just go through and you do these one at a time. So if this is f, what is your f prime? 2x, right? So that's x squared, that's not so bad, times. This is g, what is g prime?
2 plus 1, 2, wait, oh, the prime, or you're asking for G though?
G, yes.
So the
2x plus 1 to the fifth. Okay, so I differentiate the first one, leave the second one alone, right? So that's the product rule. Then put a plus sign. Then I leave the first one alone, which is just x squared. Then I multiply by
10x
the
to the
derivative of the
fourth.
second one. So this is
10x to the fourth?
Is it just the inside?
Or, no,
I think they do the outside.
2x plus 1 to the 4.
I originally got 10, in parentheses, 2x plus 1 to the 4th, and then I just kind of distributed 10, but.
take me to the first step. How do you get that?
5
So plus,
parentheses.
So 5 in the front,
5 comes down, you differentiate around it,
2x
so that's going to be the fourth power left over.
2x plus 1.
Here's 2x plus 1, and then
times the derivative of the inside.
times the derivative of the inside, which is 2. So notice here, you had to use the chain rule. So you can be using a bunch of rules simultaneously, right? So the chain rule had to happen here. Okay, and you wrote that as what?
Well, you know, multiply the outsides, so it's 10, parentheses 2x plus 1 to the 4th.
So here we have 2x times 2x plus 1 to the fifth, plus, say 10x squared to x plus 1 to the fourth.
Also, don't combine them yet, like, don't, you know, multiply them like the 10, the 5 and then 2 to get the 10. Don't do that.
I did, that's where this 10 came.
And then, okay, so before
So I
you got
multiply the
there,
5 and the 2 and the x squared, that gives me 10x squared.
and don't distribute that 10 inside.
You can't,
No,
because
before.
the inside is a fourth
Oh, okay,
power.
okay. Oh, the 3.
Right, the 10 has power 1, so you can't just move it inside the parentheses. So at this point, this is fine. I mean, there are cases where you might want to factor that expression, which you could. There's a common 2x times 2x plus 1 to the fourth that you could factor out. But at this point, we're not going to worry about that too much. It's worth mentioning though. There are times when you might want to factor, because there are times when we'd want to know, for example, where is the derivative equal to 0? And you could have factored it like that, which would give us 2x times 2x plus 1 to the fourth times 7x plus 1. So there are times when you want to write the derivative in a factored form because you want to be able to set it equal to 0 and solve for x. But for us, this is fine. Any questions on this stuff? About B. How do you differentiate that?
Do you have to do like, can I do the, since the square root of x to negative 1/2?
Okay,
Square root of x is x to the positive 1.
Yeah, positive
so we could change that to the,
2.
to x.
You have extra 1/2.
That wouldn't work because of the thing you showed us.
Come again? You're thinking of this as this, right?
That's not gonna work.
Right, and what is that?
That's 1 and 2, 1x to the 1
Are you doing the product rule? Are you doing the product rule?
I'm doing the product and then I'm gonna do the chain for the, square.
We don't actually need chain, and in this case, you don't actually need the product rule.
I suppose that how much the radical x plus 1x, I mean, 1/2 x.
Yeah, you're still doing the product rule. What is this?
It's just 1, I mean, it's just x to 1.
Is it X?
Hmm?
X?
It's not x.
That's why it's 1/2. I'm guessing.
Yeah, and what would you get? Huh? She's like the shyest one, and she's the only one saying the right thing. Yeah, so you would get what?
X to 1.
That's x to the 3 over 2.
Wait, how does it?
So if I see this, I would actually think of it as that and just apply the power rule. Right? I could simplify with algebra first, right? Remember your laws of exponents. This is x to the 1 times x to the half, multiply things with the same base, you add the powers. So I would simplify first using algebra.
Wait, how do you?
So the product rule would work at all in this one? Or
The
would-
product rule would work, it's just, it would be overkill. So technically you could have, with the product rule, so let's say with product rule, right? Here's how it would have worked out. Well, you'd have to do your f prime times g plus your f times g prime, right? So this would be 1 times radical x plus x times 1 over 2 radical x. Now, how would you actually simplify that?
Because you pretty much
I mean,
added the powers.
X over, over,
huh? This is times, what?
2
1
times
plus
x
1/2.
plus x over.
What do you mean 3 times
3x,
x?
so it's gonna be 3x over 2 square root x.
How would you get, how did you
I multiplied the denominator 2 square root of x to the 1 square root of x, and then added it to the numerator.
get? So you
and
created a
then-
common denominator, 2
Yeah,
radical
yeah,
x
yeah.
over 2 radical
Yeah,
x.
exactly.
And so here you would have 2x over 2 radical x plus x over 2 radical x. And this would give you 3x over 2 radical x. And then you can cancel this into that one to get a half power. So that gives you 3 over 2 radical x, right? Which could have gotten there easier, in my opinion. This is just x to the 3 over 2, do the power rule, right? Whereas here, you have to common denominator, recombine fractions, you know, it's kind of weird, right? So if someone were to ask you, is the derivative of this ever 0 or anything like that, then you'd have to actually go through a lot more to be able to solve or talk about that question. So this is one of the cases in which I would say the chain rule, you can apply it whenever. If you don't need to apply it, it doesn't really have any consequence. But with the product rule and the quotient rule, actually, they can get pretty complicated if you use them when you don't have to. So 1. when thinking of using product or quotient rule, check if you can simplify first. So that's one caveat I would say when using these rules. This is not a terribly complicated example, but there are some where just to just regroup after you apply a rule where you just didn't have to apply, it's really a lot of work, right? In this case, I wouldn't actually do the product rule. I would just say, hey, that's x to the third over 2. And again, all the rules that we mentioned from the very beginning of class, they are still true. They will always be true. So you need to remember your laws of exponents. You need to remember how to factor, how to add fractions. All of that is still relevant, will always be relevant. And you always want to try to apply the most basic things first. These guys we learned way before derivatives. They should kind of be the first things you want to apply. How do you differentiate that? Right. Now that's kind of obvious. Like you wouldn't use the product rule for something like that, right? Because we have a rule that says if there's a constant, you can just leave it alone, right? Now someone could say, oh, this is f and that is g, and then they go through the product rule, right? In which case, when they differentiate the 5, the answer would be 0. You kill one term anyway, and you don't be left with this. So here, don't need product rule. Don't need product rule if one factor is a constant. Right. I would just use the power rule here. Now you could do the product rule. You could have like the derivative of 5x squared, and you think of this as your f and your g, and so you have f prime times g plus f times g prime. F prime would be 0, g would be that, here f would be that, g prime would be, this was a cube. And so this part would die anyway, and you'd get back here just after wasting time. And it's also worth mentioning, a lot of the times when a student does a product or a quotient rule, when there's a constant involved, they tend to forget to put a 0 here. I don't know why, but it's just something that's always very frequently forgotten. What about D?
The quotient rule.
Okay, now this one I can't really simplify very easily, right? You have to remember how to long division of polynomials or synthetic division. So this seems to beg for the quotient rule. So I'm not going to be shy about it here. I'm going to think of this as f and that as g. And I understand that I want f prime times g minus f times g prime all over g squared. And you have to memorize that formula eventually, keep writing it down until you remember it. And so here, f prime, which is 2 times g parentheses minus f
Plus
parentheses
3.
times g prime
3
3 all over
3x minus 2 squared.
g squared. So that's the first one. Let's simplify this a little bit. It can be simplified. This would multiply out. I can distribute. This would give me 6x.
Minus 4.
Let's take that in a different color. This would give me 6x minus 4. This would give me here minus 6x minus 3. So the 6x's would die. You would get minus 4 minus 3. And so this is just minus 7 over x minus 2.
Oh, so don't, expand the bottom, just leave it.
You never expand the bottom. Yeah, that's one of the things I mentioned a while back. You want to simplify a fraction, expanding the denominator is never something you want to do. Right? You can expand the numerator to like regroup and stuff, but expand the denominator is never going to be the thing you want to do. How do you differentiate this one?
So you would do the f prime, write it into.
I can tell you right away, the answer is 1/2. If you're thinking the quotient rule, you shouldn't be thinking the quotient rule. Why? Because the denominator is a constant. That probably brings me up to the second warning. 2, don't use quotient rule with denominator as a constant. Not that it's wrong, it's just that it would make it way more complicated and students would tend to get it wrong with the extra algebra that they have to do.
Yeah, so like when the denominator is constant, you leave it, right?
Yeah, in fact, yes, if denominator is constant, to differentiate, leave the denominator alone. And differentiate the top. Right? So if a denominator is constant, you can pretty much ignore it, like completely. Just leave it alone. And the reason is, that's because of the constant factor rule. This guy I can think of as 1/2 times x, right? So now to differentiate that, I'm going to leave the 1/2 and multiply by the derivative of x. But then I can just multiply back, and the 2 just goes right back under the bottom. Right? So if a denominator is a constant, don't do the quotient rule. Just leave it alone, differentiate the top. Right? So you can alternatively, if you thought of using the quotient rule here, which I would not recommend, you would have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And so that would give you 2 minus 0 over 4, so you'll still get the half back again. And again, I could have put this here a half power, and that would be a lot more complicated to actually do that. Secondly, as again, for some reason, students often forget to put the 0 here. So if you're going to do this way, if you want to just be brain dead about it and just every time you see a division use a quotient rule, just be careful to always put a 0 here, but it's not recommended. It's very common for students, whenever they're differentiating a constant in a much larger rule, that they just rewrite the constant. So a very common mistake would be for someone to put a 2 here instead of a 0, and now the whole problem is wrong. I'm not sure why, but I see it all the time. It's kind of like that mistake with the f of x plus h, how students tend to write f of x and then put a plus h at the end. I see it all the time. I don't know why it happens, but it happens all the time. This is another thing that happens all the time. Usually when you're applying a quotient rule where one of the functions is a constant and they're doing it in this huge formula, they always forget the constant derivative is 0. So I would just not do it, just don't do it. You see the denominator is a constant, you literally leave it alone and differentiate the top. How would you do that one? Come again? Right, how did you do that?
I put x on the numerator.
Right, this is 2x to the minus 1. We actually saw something like this already. And then now, just do that. And again, so you could write this as negative 2 over x squared, that's fine. But this brings us to a third warning. Don't use quotient rule if the numerator is a constant. In this case, you can't just ignore the numerator. You need to bring up the denominator. Using law of exponents. And then use like the chain rule. It will usually be an application of the chain rule. In this case, it was the power rule, but if you can do the chain rule, it's not going to make much of a difference. And again, you could do the quotient rule here, but it's overkill. Like, why would you want to waste time writing that down? Even if you do remember to put the 0 there, this took extra time for you to write out and then read and simplify it. Like, why would you do that to yourself? Just don't do it. So these are just some warnings here. So if the denominator is a constant, you don't want to use a quotient rule. If the numerator is a constant, you don't want to use a quotient rule. In the case where the denominator is a constant, you just kind of ignore it. In the case that the numerator is a constant, you bring the denominator up and then apply the chain rule. Okay, now this one, you can't really simplify this one here. How do you deal with this? What would be your first step? You need the product rule, right? Because you have one function times another function. That's f times g. Although the first thing I would do is actually rewrite this. Right? Because we have rules that have powers in them. We don't have a rule with a radical in it. I want things to look like the rules that I have. And so I know that that should become f prime times g plus f times g prime. What's f prime here? And g? What's that? G prime. Right, you need the chain rule here, be careful. And what if I wanted to ask you to simplify this? How would you do it? Well, first of all, we could actually like cancel this 2 into that 4, so this is minus 2. But other than that,
Don't you have to put in like 4x to the third over 3 minus 4x radical, and then you get the least common denominator of the both of them?
it's probably a little bit harder. I mean, the quickest way to simplify something like this would be actually to factor. Because then it's much easier to create a least common denominator in that case. You know, in fact, you can create one without actually worrying about it. Right, so what would be the common factors here?
4x squared.
Right, so in the 12, there's a common factor of 4. There's a common factor of x. We have an x squared and an x cubed.
Because
We also have a common factor of the 3 minus 4x, right? What power do I pull out? 3 minus 4x, what power of that do I pull out? What's the rule when you're factoring? Okay, so here I had an x squared and x cubed. I pull out an x squared. How did I make that choice? What power do I pull out? The lowest power. That's the rule. You want to factor, you always pull out the lowest power. That's what you should be thinking in your head. Pull out the lowest power. 3 minus 4x is a common term. That gets pulled out. What's the power? Negative 1/2. Because the comparison is between positive 1/2 and negative 1/2. That's smaller. Now you write what's left over on the inside. So here's the 12. I took out a factor of 4, so there's a 3. I took out the x squared, so that's gone. I took out, here I had a power of 1/2. I took out a power of negative 1/2, so what power is left over? So you know you pull out the lowest power. Remember, how do you get the powers of who is left over? You subtract the power that you pull out. So I would take positive 1/2 minus a negative 1/2. That's just adding 1/2. That would give me the power 1. Plus 4, I took out x, there was an x cubed. I took out 2 factors, so there's 1 factor left. There's also a minus 2. And there's also, I took out this entire thing. So I have that left over. I can also simplify this. If I multiply this out, this will give me 9 minus 12x. This will give me minus 2x. So ultimately I get 9 minus 14x. That would be the answer. You can also notice here that the common denominator just pops up once I just take this part and move it down the bottom. Right? That would be the common denominator. But now the numerator is also going to be simplified. It's going to be factored. So we'll stop there. Try these at home. And I think so we'll stop there. Next time we should be finished with everything we want to do with derivatives. So that's nice. And we'll go on to the next section, which is on matrices. So that's going to be the easy part of the class, the last section. No more calculus. The problem with the last part of the class is more like arithmetic. You're going to be adding a bunch of numbers, but it doesn't really get more complicated. So we'll stop there. I'll see you guys